All right, so we move into chapter 7, and symmetric matrices and quadratic forms are the major topic here in chapter 7. That is the major topic. Now let me see here. I want to just, yeah, there's the book. There it is. So they talk about satellites that collect data around the world and a little more than, so this is just the intro to chapter 7. Every one of our chapters, as you know, has sort of an introductory, interesting problem that relates to what's covered in the chapter. And here they're talking about satellites. So what do satellites do? They collect data and they collect images. And they make a comment in the second paragraph that these Landsat images from these Landsat satellites are useful for many purposes. Developers and urban planners use them to study the rate and direction of urban growth, industrial development, and other changes of land usage. For instance, the hold on here. Hold on. And then governments can detect and assess damage from natural disasters such as forest fires. Hold on here. Lava flows, floods, and hurricanes. And the thing is, what generally we like to do, hold on here, I have too many things open here. Let me close a few windows here. Okay, so the data that's collected has to be organized. And again, you want to remove any type of redundancy in the data. All of this relates to a topic, well, it relates to a topic they mentioned called principal component analysis. Okay, and if you go into the statistics field, certainly, you will learn about principal component analysis. Okay, it's an effective way to suppress redundant information and provide images of most of the information from the initial data. And in order to do that, we need to understand the topics that come up in chapter 7. I wish we would have time to cover all of chapter 7, but we just don't in this course. But the next course that you take in linear algebra will get into these kind of ideas. So if we continue here, okay, here they talk about images, but I want to get to right here. Okay, symmetric matrices arise more often in applications in one way or another than any other major class of matrices. Okay, so like in statistics, we have what are called variance and covariance matrices that measure how variables change in relation to other variables. Those are symmetric matrices. And symmetric matrices actually have extremely nice properties. So first of all, what is a symmetric matrix? A symmetric matrix is a matrix such that the transpose of the matrix is equal to the matrix. Therefore, you have to have a square matrix. And in example 1, they give examples here of 3 symmetric matrices. Okay, 3 symmetric matrices. So if you take the transpose of those matrices, you will get the matrix back. And you notice how if you look along, for example 1, where those 3 symmetric matrices, if you look along the diagonal, the matrix is symmetric about the diagonal entries. Okay, so like for instance, let's take a look at this second matrix. Okay, the diagonal entries are 0. I don't know if I can just, yeah, okay, 0, 5, and -7. So along that diagonal, like where the -1 is, the -1 is, there's a -1 in the second row, first column, but there's also a -1 in the first row, second column. There's an 8 for that symmetric matrix, the second one in example 1. There's an 8 in the third row, second column. There's also an 8 in the second row, third column. See, those are symmetric matrices, and if we take the transpose of those matrices, it equals the matrix. Now below they have examples of non-symmetric matrices. So of course any matrix that's not square, not an n by n matrix, would be non-symmetric. And you know, those, they just give examples. So they're non-symmetric matrices. The entries across each other along the diagonal are somewhere they're not equal. Okay, so they these symmetric matrices have incredibly nice properties. So they mention here, if possible, diagonalize the matrix. Okay, now what I want to do, I'm going to go right to the notes on this. I'm going to go right to the notes because I have very nice notes on this. So let me see here. Let me go to our notes. Okay. Okay, so this is really an example discussion, but let me give you a moment to copy down up to here. Okay, and then we'll talk a little more. Okay, so we are dealing here with symmetric matrices, and this matrix A is symmetric. If you take the transpose of that matrix, you're going to get the matrix A back. In other words, we just hold on, let me get the font down a little bit. Okay, so A transpose equals A. Therefore, A is symmetric. Now, the eigenvalues and eigenvectors, which you can easily find for this matrix A, are given here. There are 3 distinct eigenvalues and therefore 3 distinct eigenvectors. And you know from what you learned back when you learned about eigenvectors. Now, one moment here. This was back in section 5.3 about diagonalization, that if the multiplicity of an eigenvector is equal to the dimension of its eigenspace for every if the multiplicity of an eigenvalue equals the dimension of its eigenspace, then if you have a matrix, with eigenvalues, and for every for every eigenvalue, okay, the dimension of the eigenspace equals the multiplicity of the eigenvalue, then A, the matrix A, can be written as P times D times P inverse. This is called diagonalization, section 5.3. The matrix P consists of, it's a matrix whose columns are the eigenvectors, and the matrix D is the matrix, square matrix, of course, whose values are, whose diagonal consists of the eigenvalues. Of course, the order of the eigenvalues has to match the order of the eigenspaces in the matrix P. Now, what we want to do here in this case is we want to find a matrix P and a matrix D such that A equals P times D times P transpose. We already know for this problem, okay, hold on here, let me just, yeah. So we already know, if I go to the next page here, that this matrix P, with its eigenvectors as its columns, and this matrix D with the corresponding eigenvalues, we know that A will equal P times D times P inverse. And note here that the eigenvectors V1, V2, and V3 are orthogonal to each other. And that is no accident. That is no accident. When you have a symmetric matrix, any two eigenvectors from different eigenspaces are orthogonal. They are orthogonal. I will show you that quick, and then I'll come back to this. Let me show you that from the book. That's worth you seeing, I think. Let me just go down here. Yeah, so I'm gonna go back to that. I know you were copying, but I want to show this to you. So notice, if you notice, the eigenvectors for that symmetric matrix A were orthogonal, and that's not an accident. By theorem 1 in section 7.1, if you have a symmetric matrix, then any two eigenvectors from different eigenspaces are orthogonal. And it's not hard to show that. They have a proof. They have a proof here. What they say is, okay, suppose you have two eigenvectors from a symmetric matrix that correspond to two distinct eigenvalues. Well, if those eigenvectors are orthogonal, the dot product will equal 0. So what they do is they say, okay, let's consider the lambda times the dot product of V1 with V2. Let's consider that. Well, that can be written as lambda 1 V1 transpose times the vector V2. And of course, so lambda 1 times V1 equals A times V1. So lambda times that dot product equals the transpose of AV1 times V2. But remember, by transpose rule, if you have the transpose of a product of vectors, that equals the products of the transposes of the vectors, if you have the transpose of a product of two matrices, that equals the product of the transposes in inverse order. Okay, and so you end up getting this. All right, but A transpose is equal to A because A is symmetric. So then the eigenvalue times the dot product will equal V1 transpose times A times V2. But remember, A times V2 is, since A is V2 is an eigenvector, A times V2 is equal to lambda 2 times V2. And that gets us down here. But we can factor out the lambda 2. And so lambda 1 times the dot product of V1, V2 equals lambda 2 times the dot product of V1 with V2. Well, if you subtract lambda 2 times that dot product to the left side, okay, you're going to get then of the equation, you're going to get lambda 1 minus lambda 2, that quantity, times the dot product equals 0. But we assume that lambda 1 was not equal to lambda 2, right? And so because of that, the dot product of those two vectors from different eigenspaces have to be orthogonal, because the dot product equals 0. So the vectors v1 and v2, those eigenvectors from the different eigenspaces, are orthogonal. So essentially, the eigenbases that result from a symmetric matrix are orthogonal to each other. They're orthogonal subspaces. Okay, and so there you go. Are there any questions on that before I go back to the notes? Okay, let me go back to the notes here. Well, here's the problem, Mikhail. P here, let me just see here, I'll write it. This P here, gosh, it always changes that font to 5 point. Really should be 3 point. This P here is not orthogonal. An orthogonal matrix, what is an orthogonal matrix? An orthogonal matrix is a matrix U such that it's a square matrix, and the inverse of U is equal to its transpose. But that's only going to happen if the column vectors of the orthogonal matrix U are orthogonal, and they have to have length 1. So what you have to do, see the P inverse here, if this is your matrix P and this is your diagonal matrix D, yes, A equals P times D times P inverse, but A will not equal P times D times P transpose. What you have to do with the matrix P is you have to normalize all those column vectors. Now, since this matrix P, since you have 3 distinct eigenvalues, that means automatically that the column vectors that are the eigenvectors of the matrix P, they're automatically linearly independent because they're orthogonal to each other. But if you want the orthogonal matrix P, you have to in this orthogonal matrix this matrix P is orthogonal, because it's a 3 by 3 square matrix. The column vectors are orthogonal to each other, and they're of length 1. In that case, A will equal P times D times P transpose. It will. Let me see. Hold on. There's a comment here. P is orthogonal. D is not. So yeah, D is just the matrix that's a diagonal matrix, right? D is called a diagonal matrix because the only non-zero entries although you could have a zero entry, but it's a diagonal matrix because all the entries off of the diagonal equal 0. That's a diagonal matrix. The original eigenvectors are orthogonal, Mikhail, but they're not orthonormal. Now, when you scale those eigenvectors so that they all have length 1, you get orthonormal. And in this case, P times D, A equals P times D times P transpose. And why does P inverse equals P transpose in the second case? Is because P is an orthogonal matrix, and so P inverse equals P transpose. Now, this is actually a very wonderful thing because inverses are time intensive to compute. Okay, they take a lot of work to compute the inverse of a matrix. Okay, and particularly if you have a matrix that has 1,000 rows and 1,000 columns, or 10,000 rows, 10,000 columns, a big data matrix where you have an image and you're storing coordinates and so forth to create the image. If you need to do the inverse, it can be very computer intensive. Okay, but if you find the inverse by just taking the transpose, that's easy, right? So we like that. And symmetric matrices, any symmetric matrix A can be orthogonally diagonalizable. In other words, any symmetric matrix A, if it's a symmetric matrix, then a orthogonal matrix P and a diagonal matrix D will exist such that A equals P times D times P transpose. Under what conditions would matrix A be orthogonally diagonalizable? The answer is when A is a symmetric matrix. And that is theorem 2, actually, in the book. When A is a symmetric matrix. Hold on, let me just make this a little nicer. And remember, if A is symmetric, it also, by default, has to be a square matrix too. Not all square matrices are symmetric, but all symmetric matrices are square matrices. Okay, are there any questions so far? Okay, give me a thumbs up if you're feeling good so far. If you're comfortable with the material so far. Wonderful. Marcellin's good. Bellin's good. David's good. Jacob's good. Wonderful. Wonderful. Excellent. Excellent. Okay, well then let's go ahead to the next page if we can. Let's look at an example then. Okay. Let me give you a moment to copy this example down. Okay, so here we have this matrix A, 3 by 3 matrix. And here's the diagonal. Okay, consisting of 3, 6, and 3. And if we look at the bottom triangle and the top triangle, they're mirror images of each other. So this is a symmetric matrix. Okay, it's a symmetric matrix. Now you're given two eigenvalues, and we want to orthogonally diagonalize the matrix. We're given two eigenvalues. So, okay, you know how to do this. You know how to do this. We have to find the eigenbasis for each eigenvalue. So for the first eigenvalue, well, let's just, I'm putting in a lot of detail here for you. So again, what do we want to do? We want to find the orthogonal matrix P such that A equals P times D times P transpose. We know since A is symmetric, then those matrices P and D exist. First thing we want to do is find the matrix P. And recall from your knowledge from section 5.3, to construct that matrix P, we need to find the eigenvectors. Let me give you a moment to catch up here. Now, what you're seeing, by the way, this example is section 7.1, where we're going to orthogonally diagonalize this matrix A. This example, I'm showing, I'm basically working it out by hand. And for your final exam, although you're going to be allowed to use MATLAB to help you a lot because you know how to do row operations, for these section 7.1 problems, I will ask you to show your steps, row reduction, row operations, and so forth, just so so I can see that you understand the full process. This problem that we're doing here brings together a lot of the concepts that you learned in the course. And, and so naturally, I would like to see that you fully understand those concepts. Okay. And that's just, part of showing understanding. So, okay, so we need to solve the augmented matrix. Okay, this augmented matrix here, when lambda 1 equals 7. So I set it up, and we are going to use this -4 here as a pivot. So I want to get this 4 down here. I want to make it a 0. So I'm just going to add the first row to the third row and place the third row by that result. Please let me know if you have any questions, okay? Please let me know. Well, all we're doing here, Michaela, are row operations. all we're doing are row operations. And to find the eigenbasis for, or the eigenspace for the eigenvalue lambda1 equals 7. Next thing I'm going to do, by the way, is I'm going to switch the first and second rows. I don't know about that. I'm not sure, but you know, this is a very general thing what we're doing. Okay, no problem, Mikhail. Okay, so we're going to switch the first and second rows so that we can get, I just intuitively, since I'm working this out by hand, I want the -2 here as a pivot. Yeah, triangular matrices, it's easy to find the eigenvalues. That's right. That's right. But of course, we don't have that here. So, okay, we'll switch the first and second rows, do a row swap. And then I'm going to take -2 times the first row, add to the second row, and replace the second row by that result. So there's nothing here that's complicated, these row operations. And row operations help us remember, it just helps us not lose our way, so to speak, with these concepts. Okay. How many have heard the expression, if you don't use it, you lose it? How many have heard that expression? Yeah, David's heard of it. And so, you know, the row operations have a lot of meaning to them. Basically, well, basically the row operations, you are rewriting the system of equations into an easier system of equations. And yeah, and if we forget how to do that, it makes the mathematical underpinnings of what we're doing, we just sort of, it's not as intuitive anymore. And we want intuitiveness. We want intuitiveness here. So, okay, now what I'm going to do is this -2, I'm going to multiply by -1/2 the first row, so I can get a 1 there. And now, okay, we have here's our augmented matrix. And okay, so it looks like we have a free variable. Okay, it looks like we have, so let me just kind of put the dashes here. Augmented matrix. We have 2 free variables, x2 and x3 are free. And then x1 is -1/2 x2 plus x3. And now we can construct find the eigenvectors. So we take the vector x in the eigenbasis and write it in parametric vector form, right? I don't want you to forget how to do this. This is important. We write that eigenvector, all eigenvectors in the eigenbasis can be written in parametric vector form. And so this is going to then tell us, okay, we have an eigenvector, I'll call it x1 here, and an eigenvector x2 here. Okay. But if you don't mind, for x1, I'll use the multiple of you know, this eigenvector here, since there's a fraction that equals a -1/2 in there. I'll multiply that eigenvector by -2. And so that'll get us, sorry, I'll multiply by 2. So we could use the eigenvector -1, 2, and 0. Okay, so maybe I'll use that as my eigenvector, one of the eigenvectors, and I will actually. Are there any questions so far? Okay, so let's use the -1, 2, 0. Let's let that be one of the eigenvectors, and the 1, 0, 1 be the other eigenvector for the eigenspace corresponding to λ1 equals 7. Okay. So here we are. Here's a basis for our eigenspace. Okay, there's our basis. Okay, all right, Jacob. All right. Okay, so now let me ask you this. Are vectors x1 and x2 orthogonal? That's correct, Mikhail. Since the dimension of this eigenspace here is equal to 2, the eigenspace corresponding to λ1 equals 7, then the dimension of the eigenspace corresponding to λ2 equals 2 would have to equal 1. In other words, the basis consists of one eigenvector. I mean, we know this symmetric matrix is diagonalizable. Okay, so but notice the vectors x1 and x2 are not orthogonal. They're not orthogonal. So we're going to have to remedy that later on, because for the matrix P, for P transpose to equal P inverse, okay, we need, for P to be an orthogonal matrix, the eigenvectors of P have to be orthonormal. Okay, and you know, right now we don't have two. The vectors x1 and x2 are not orthonormal. They're not of length 1, and they're not orthogonal. But let's go ahead and move on and get the other eigenspace. We'll come back to that. Let me ask you this. Let me ask you this while I'm in the neighborhood. If we have this subspace, that's the span of those two eigenvectors. It's a two-dimensional subspace with that basis vectors x1 and x2. How can we get, and the span of those x1, x2 vectors is a plane, right? It's a plane in three-dimensional space. How can we get a basis, an orthogonal basis for that space? The span of x1 and x2, those vectors, is a plane in three-dimensional space. Okay, that's right. So what we're going to have to do, Mikhail's right, we're going to have to come back and use Gram-Schmidt on these two vectors, on that subspace, in order to get an orthogonal basis. But for now, I mean, this problem has everything in it, right? A lot of stuff you learned. So now let's go after the eigenspace corresponding to λ2 equals -2. So I just choose to swap rows 1 and row 2. That way I have this -2, the smallest number at the top, as a pivot. Of course, you know, with partial pivoting, we use the largest number in a column as the pivot. But as humans, we use the smallest number. Now what we're going to do is we're going to take -1/2 times the first row and replace the first row by that result so I can get a nice number 1 here as the pivot. Okay, so what we're going to do now is to produce zeros. We want to get this augmented matrix in reduced echelon form. So to do that, we need to get zeros where the 5 and the 4 are. So we'll use the 1 as a pivot. Okay, so continuing on, if everybody's good here. Okay, so what I do is I take -5 times the first row and add it to the second row, and -4 times the first row and add it to the third row. And that's going to generate then this nice matrix here. Turns out the second and third rows are the same. So I can just take -1 times row 2, add it to the third row, replace the third row by that result. And again, I just do the normal steps then to get the matrix into reduced echelon form. And again, on the final exam for these section 7.1 problems, you can be sure you're going to get a problem like this. I want you to work it out by hand. Okay, I want you to show the steps, show the row operations, show the whole process. Okay, so this then, we're going to get one free variable. X3 is going to be free, and the basic variables are X1 and X2, since they're written in terms of the free variables. Now we write the eigenvector in, I'll call it eigenvector X. We write it in parametric vector form. And pull out that free variable. And for your eigenvector x3, okay, I mean this is any multiple of this vector here with components -1, -1/2, and 1. Any multiple is an eigenvector. So why not multiply by 2? Okay, and so then use x3 as your eigenvector. So there's a lot to this problem. Okay, a lot to this problem, a lot of stuff. I mean, this problem would be worth some big points on the final exam, right? All right, so let's pause for a moment now And, let's construct matrix P and matrix D with what we have. So matrix, well, here's the basis for the eigenspace corresponding to lambda 2 equals -2. And we can choose to construct matrix P with the 3 eigenvectors that we found. Notice that the eigenvectors for the first eigenspace, okay, notice that those eigenvectors are orthogonal to the eigenvector in the second eigenspace, and we saw the proof of that. Okay, but if P is equal to this matrix and D is equal to that diagonal matrix, notice I got 2 entries of 7. They come first because my eigenbasis for lambda 1 equals 7 came first. Sure, A will equal P times D inverse. A is diagonalizable, but A, with this choice of matrix P, A is not orthogonally diagonalizable. It's not equal to P times D times P transpose. Now, why is that? Why is that? What's one thing you can tell me about the columns of matrix P? The lengths. What are the lengths not equal to of those column vectors in matrix P? That's right, they're not equal to 1. But also another problem too. The vectors, like we mentioned before, for the first eigenspace, the vectors 1, 0, 1 and -1, 2, 0, they are not orthogonal to each other. So for that eigenspace, we need to create an orthogonal basis for that eigenspace. And that's where Gram-Schmidt's going to come in. So let's go ahead and continue here. Okay, so these notes, I'm really trying to spell things out for you very clearly. So we need the columns of the matrix P to be orthonormal for the matrix P to be an orthogonal matrix. And like I said, the dot product of x1 with x3 and x2 with x3, those dot products are 0. Those vectors are orthogonal because eigenspaces of a symmetric matrix are mutually orthogonal. That's by this theorem 3. Actually, it's not theorem 3. It's actually theorem 1. Not theorem 3, theorem 1. But again, inside the first eigenspace, even though the vectors x1 and x2 form a basis for that eigenspace, they're not orthogonal. So we need to get an orthogonal basis for the span of those eigenvectors. That's the eigenspace, right? And we're going to use the Gram-Schmidt process, which you're familiar with. Okay, so the Gram-Schmidt process, what we do is we let we're going to keep one of the eigenvectors. So we'll let V1 equals X1. Okay, then the, hold on here. One moment, going back, coming forward. Okay, so the second vector that would be orthogonal to the first vector for this eigenspace, you know, based on the picture here, you take the second eigenvector and subtract the projection of the second eigenvector onto the subspace W. Subspace W is the span of the eigenvector x1. So this here, let me see, I just want to write it. This here is the projection of the vector x2 onto subspace W. So one way to kind of maybe do this is to write it like this: V2 equals x2 minus the projection of vector x2 onto subspace W. And then go from there to here. How many draw little pictures to help them with the Gram-Schmidt? Is that helpful? I hope it is. Yeah, Mikhail, mental image. Well, yeah, oftentimes I like to draw stuff on the paper, but sure. So now we're going to find that second. Right, that's right, Mikhail, that's right. Now we're going to find that second eigenvector. But are there any questions up to this point? We're going to find, no, I'm sorry, we're not finding eigenvector. V2 is not, I want to say this the right way. I'm just trying to find, I have a subspace that's formed by the span of two eigenvectors. It's a two-dimensional subspace of R3. I'm trying to find an equivalent I'm trying to find an equivalent basis for that eigenspace, okay, but an orthogonal basis, and that's what I'm doing. Okay, so the vector v2, that's right, vector v2 is part of the orthogonal basis. That's right, Mikhail, that's right. So, okay, here is v2. And this, again, I want to see this work on the final exam, okay? I don't want anybody not getting the grade they should deserve because they didn't show work for a particular problem, right? It isn't just getting the answer right. I need to see the work for these section 7.1 problems because it's new material, you're being tested on it, and I need to see that you understand the process. So, all right, good. I want everybody to succeed. All right, so you get this vector v2, and again, as is traditional, you end up with a vector with a bunch of fractions in it. Well, we can just multiply by 2 and remove those fractions, and that'll get us vector v2. Now, well, I'm calling it V2 prime. So vector V1, V2 prime forms an orthogonal basis for that eigenspace corresponding to lambda 1 equals 7. So let me see. For this, what was it? V1 was equal to 101. And V2 is negative 4, 1. This is V1. This is V2 prime, sorry. And yep, those vectors are orthogonal for sure. Now what we do is, to get the matrix P, we have to normalize these, we have to normalize the V1 vector. So you divide by square root of 2. We have to normalize the V2 prime vector. Well, the length of that vector is square root of 18, so you divide all the components by square root of 18. And then the vector, the eigenvector corresponding to the second eigenspace, the length of that vector is 3. So you normalize, okay, that vector so that has length 1. And if this is your matrix P and this is your matrix D, you can verify that A will equal P times D times P transpose. You can check that in MATLAB and you'll see that's true. All right. Are there any questions at all? I remember in linear algebra, I had to do this process, but I think I had to do it for a 4x4 matrix. But I remember doing it on my final exam. I mean, this is really quite a beautiful process. The fact, look at all the factorizations that we've had for matrices. A matrix A can be written as an LU factorization. A matrix A can be written as, what is it? QR factorization, A equals Q times R. Here now we have yet another factorization, P times D times P transpose. Okay, now that's true only if you have a symmetric matrix, though. But the point is, these factorizations lend themselves to different beautiful applications. Okay, are there any questions on this before I return to the book? I want to do a little bit more from the book, and then I think we'll be good with this section. Give me a thumbs up if you're feeling good with this process. Good. Marcella's good. Jacob's good. Wonderful. How are you feeling, Fatima? Are you good? Wonderful. Wonderful. Okay. Belen, how about you? Good. Good. All right. All right. So, okay, let's now go back to the book and look at a few more things. Let's look at a few more items. So, okay. The set of eigenvalues of a matrix A is sometimes called the spectrum of a matrix A, and I have heard this term used in other courses. And there's what's called a spectral theorem for symmetric matrices. So the properties in the spectral theorem in theorem 3 have to hold. Okay, a symmetric matrix has these properties, has those 4 properties. And property B, the dimension of each eigenspace for an eigenvalue equals the multiplicity of the eigenvalue. I mean, that's, you know, that's great, because that means you can diagonalize that matrix A, right? Also, by part C, the eigenspaces are mutually orthogonal. That's beautiful. And you know, it's really such a wonderful thing. And the beautiful thing is too, in nature, a lot of matrices, particularly like in statistics applications, where you're doing data analysis, matrices, like if you're looking at variances and covariances of variables, those matrices are symmetric. And it just lends itself to so many beautiful, wonderful things. I wish we had a chance to cover the rest of this chapter 7 in the book. But at any rate, you know, you can look at it on your own if you like. Let's continue on. Let's continue on. So there is something called a spectral decomposition for a matrix. A spectral decomposition. Okay, so again, we're supposing that we have a symmetric matrix, okay, and A equals P times D times P transpose. Well, the matrix P consists of those orthonormal column vectors or orthonormal eigenvectors. Well, I want to be careful. Orthonormal columns U. Diagonal matrix D is a diagonal matrix of eigenvalues. And then P transpose is just this matrix here. Now, you can write this matrix product this way. You can, you know, the eigenvalues, when they're on a diagonal like that, they're treated, you can think of them like as scalar coefficients. So let me show you an example of this. So like if you have, I'll just give you an example here. Okay, so if you have a matrix like 1, 2, 3, and 4, and you multiply it by the diagonal matrix with like a 3 and a 5 here, okay? Okay, so this is a 2 by 2 times a 2 by 2. Okay, so this is going to equal 1 times 3 plus 2 times 0. And then we have 1 times 0 plus 2 times 5. So I'm using the row column rule for matrix multiplication here. 3 times 3 plus 4 times 0, and 4 times 0, no, 3. Hold on, let me just check one thing here. Yep. We have 3 times 0 plus 4 times 5. Okay, so this then, this here, is going to equal, well, I want to say it the right way. It's going to equal it's going to equal this matrix. Okay, the first column is going to be 3 times the vector 1, 3. And the second column here, let me just make sure I have this right. Yeah, second column is going to be 5 times the matrix 2, 4. See that? There's the matrix 2, 4. Or the vector 2, 4. Okay, so when you have, like if you have a matrix with column vectors u1 and u2, and you multiply it by a diagonal matrix with diagonal entries lambda 1 and lambda 2, that's going to equal lambda 1 times the vector u1 plus lambda 2 times the vector u2. No, that's not right. It's going to equal the matrix with columns lambda 1 u1 and lambda 2 u2. And that's demonstrated. I mean, it's demonstrated with this little nice example here. All right, are there any questions on that? Because if you're comfortable with that, then we can go back to the proof at hand. A lot of times when I see things in proofs, I like to think of little examples to kind of help me feel comfortable with what they're writing. Just double checking everything. Right. So this here would be like lambda 1, and this would be lambda 2, and so yeah, it works. It's just fine. It's just fine. So let's go back here. So now this brings us down to this step here. And if we multiply those matrices, we're going to get the matrix A written as the sum of these matrices. U1 times U1 transpose, U2 times U2 transpose, UN times UN transpose, That's called the spectral decomposition of A. And this is a big deal. This is a big deal if you go on further in matrices and you know, and in fact, I'm going to say this right. Every matrix where you take the uj times uj's transpose, that's going to be a projection matrix. Because if you take uj times uj's transpose and multiply it by the vector x, that's actually the orthogonal projection of the vector x onto the subspace spanned by uj. Now that's shown in an exercise, and I believe that'll show up in your homework. But the point is, you can express the matrix A as a linear combination of these projection matrices onto the of the vector x onto these subspaces spanned by the different vectors, the different u vectors. So how would we do a spectral decomposition? Well, here they give an example. So here's a matrix A, okay, and they're 2 by 2 matrix, and they are giving you the orthogonal, they are showing you the orthogonal diagonalization of that matrix A. And so the matrix A can be written by this way, okay, by the spectral decomposition, well, by actually this formula here. Okay, let me just sort of take off a few things. Right, so in example 4, by that formula 2 above, the matrix A can be written this way, and you compute U1 times U1 transpose. So that's a 2 by 1 vector by a 1 by 2 vector. That gives you a 2 by 2 matrix, right? And similarly, U2 times U2 transpose gives you a 2 by 2 matrix. And so you can write the matrix A as the sum of those 2 by 2 matrices. That's called the spectral decomposition of the matrix A. And I have seen that in other courses that I have taken. So I'm sure it'll come up for you as well. I mean, this is it's so beautiful what you're seeing. It's just amazing how beautiful this material is. Truly, truly beautiful and so useful. Are there any questions at all with section 7.1 before I stop the recording? Cameron's good? All right. Okay, so let me stop the recording then. If everybody's good. Excellent.